Okay, so 11 is a little bit tricky. It is a calculator problem denoted with this star here. What's tricky about it is that I'm working backwards to obtain this point. It says, which of the following is an equation of the line tangent to the graph of this following function where the slope at x is equal to 1. Okay, so my at is unknown. Now we know the equation of the tangent line. We need a point, we need an xy, and we need a slope. We need some kind of f prime of x, a slope that occurs at the specific x. In this case, we're given that as 1. But we don't know the x and we don't know the y. So we're working backwards to obtain that point. Now, this is the first calculator problem that you have on the review, and I want to make sure that you know how to set up your calculator and how it should always be set up. I have told you about y2 and y3 and how to set up these derivatives automatically so that all you have to do is input a function. What I've discovered is that this will reset if nothing is inputted into y1. So it's helpful to have x always in there waiting for something to be inputted. Because as soon as you delete it, this bold will go away and it'll reset to its normal default. Okay, so let's go ahead and get started. So if we have this function here, we know that this derivative will equal 1 at a certain point. So to find where it's equal to, what we're going to do is we're going to put this function in the calculator. I'm going to show you how to efficiently use this graph. So x to the fourth plus 2x squared. So x to the fourth plus 2x squared, whoops, x to the fourth, let me clear this real quick, x to the fourth, right arrow to jump down, and then it's plus 2x squared, so plus 2x squared. Seem to be struggling with these buttons just a little bit. Okay, so that's y1, and you see how it, as soon as we inputted or cleared it, what it did was it reset this back to its default. Now I'll have to rebold it. So like I was saying, you might want to keep it as x always or have something in that function. Okay, so now you notice how there's not a black square here. There's not a black square here as highlighted here. That means only one will graph right now. Okay, so to make sure that the derivative graphs, I can turn it on by hovering over and pressing enter on the equal sign. Okay, I'm going to go to y4 right now, and I'm going to go ahead and put a value of 1. And the reason why I'm going to do that is because I have three functions going on. I have the position function that will be graphed, I have the derivative function, which is my f prime, and I have y4 is equal to 1. The only reason why I put it at y4 is I don't want to overwrite these already preset forms. So what is it that I want to show? Well, I want to show where the derivative of the slope of 1 is equal to the derivative of this function. Okay, so if I take this and I say f prime of x is equal to 4x cubed plus 4x, this function should be equal to the one that was given to us. Now this function, instead of putting it by hand, I can just make sure that the second graph is on and that it actually graphs. So I don't need the position function to actually graph, I just need it inputted into my y1 so that my y2 can calculate and it can graph. Okay, so there's many ways to do this. I'm just trying to show you different variations as far as how you can use this calculator. Alright, so y is equal to 1 will now graph, so only y2 and y4 will graph. So when I go zoom 6, let's let that populate, and as we're letting it populate, let's remind ourselves why we're looking at these graphs. We're looking at this as f prime of x, and then here comes y is equal to 1, the f prime of x that was given to us. So now we're going to find the at. When I second calc 5, that's the intersection, first curve, second curve, and guess, so I can just press enter, enter, enter. It will tell me what this x value is. Now understand that this is the intersection between two derivatives. So this y is not the y's position. Like when I come over here and I look at this y, that is not what I'm obtaining from here. The only thing that I'm obtaining is the at. Okay? So 0.237-ish is the at, 0.237. because I obtained it from the derivative function that we graphed and also the one that was given to us, that point of intersection. So I'm going to put this 0.237 into my original function so that I can obtain this position y value. Okay, so that is a lot that's going on. But, I mean, you can rewind and see what's going on step by step. So 0.237 is going to be inputted into this function. Alright, so second table, we're going to look at the tables that we have. And notice when we go to the table, only y2 and y4 are showing up. Because on y1, or my y graphs, those are the only two that were accessed. So I will now turn on this one, go to the table, and now my y1 position function has showed up, to where if I put this 0.237, I obtain the y value of 0.115-ish. So 0.115 is that y value. Now I have my point. 0.237, 0.115. So this is a medium to a medium difficult problem because of the concepts that are going on, you working backwards to try to find that point. So y minus y1 is equal to my given slope of 1, and it's going to be x minus x1. Now remember, this x1 that we found was our at, the intersection of my derivatives, but it also gives me my input throughout. So x minus 0.237, and then when I multiply it out and move it over, I'm going to have x minus 0.237, and I'm going to add that 0.115. This will be what y is. So negative 0.237 is going to add with 0.115, and I'll get negative 0.122, which gives me the answer of D.